Graphs help you picturize functions. In the previous lecture, we looked at some rather simple examples. In this lecture, we're going to take more interesting and somewhat more difficult functions. In particular, towards the end, we'll consider a function that's almost unplottable. Let's begin with a function that has different forms for different values of x. F of x will be defined to be plus 1 if we are on the left side, which means x is negative. It's 0 if x is equal to 0, and it's minus 1 if x is towards the right, in other words, if x is positive. Well, the first point over here is easily plotted. At x equal to 0, y is 0, or f of x is 0. And now we can see what it looks like as we move from the left towards the right. So x goes from more negative to less negative and gets close to 0. The value of f of x stays at plus 1, and then it suddenly jumps to minus 1. And so you see, this is the plot of the function up over here. Now let me change this function slightly. Here's a function that's almost the same. F of x is defined to be plus 1 for x negative, but I'm going to define it to be 1.5, 3 by 2, if x is equal to 0, and to be minus 1 if x is positive towards the right. Now, that means that this point over here, 1.5, is going to be the value at x equal to 0. All right, so the function looks identical. What we see is that it comes in, and here it is. What we see now is that the function is plus 1 over here, it's minus 1 over here, and here it is 1.5. Now, that's a very strange looking function, isn't it? Because as we come in this way, it would seem that it would go to 1, but instead it went to 1.5, and as we come in this way, instead of going to minus 1, it's gone up to 1.5 here. Let's now plot this function f of x equals magnitude of x, or the modulus of x. It's defined as follows. F of x is made up of 3 parts, of course. It's x if x is positive, that is to say if x is on the right. It's 0 if x is 0, and it's minus x if x is negative. So note that whenever x here is negative, minus x will be positive, and so therefore f of x is always going to be positive. Now let's see what this looks like. You will not be surprised to see that this is a straight line to the left and a straight line to the right. Of course, that's very easily understood because here we have f of x equals x, and that's this straight line which has got slope equal to 1. On this side, we have f of x equal to minus x. That's a straight line with slope minus 1, and you can see that the function is positive everywhere. Here's a slightly different function. F of x equals magnitude of x minus 1. So obviously when x is equal to 1, this function is going to be 0, and of course it's always going to be positive. And now you can expect that it's going to look very similar, except that when x is equal to 1, that's when it's going to be 0, and then it's going to go up. like this. All right, now let's change this a little more. Here's f of x equals magnitude of x minus 2, x minus 3, x minus 4, and x minus 5. Okay, now let's go back. X minus 4, 3, 2, 1, 0, minus 1. So when x is equal to minus 1, this function is 0. And you see that it'll go all the way to the left. Let's quickly review a bit of trigonometry. So here's a circle which has radius a. There's a point that moves up like this along the periphery. So let's say that it has moved to this point, which we can call anything P, and we draw this line. This line is the radius. It has size a. We drop a line down. That line has length P. This distance from here to here is Q. And then we define sine of x, where x is this angle, to be P divided by A. Cosine of x we define to be Q over A. And tan of x to be sine over cosine. So sine of x over cosine of x, which is P over Q. Now, of course, you can look up the values of sine x, cosine x, tan x for any value of x. But what if x is close to 0? Well, then you don't need to look up a table. You can see immediately that P is going to be very, very small. Q is going to be the same size as A, in which case sine of x is going to be close to 0. Cosine of x, you can see from the definition here, is going to be 1. And tan of x, for x very, very small, is going to be 0 as well. Now, what if x is close to pi by 2? In that case, this point here will have moved to this point here, and so you will have the angle x very close to pi by 2, in which case you can see that P would be very close to A, Q very close to 0, and from here sine of pi by 2, well, let me write it, sine of x, x is very close to pi by 2, will be 1, and cosine of x will be 0. Tan of x, now you see this is going to be something close to 1 over something close to 0, so that's a very, very large number, and that's what we call infinity. There's one other point before we go to plotting sine of x, cosine of x, and tan of x. So here is x, and then again you remember it's P. This is A, Q. Now, what happens when x goes to x plus 2 pi? In other words, if this point goes around the circle all the way like this and comes back to this point here, so you go from here and you come back here after going around once, in that case P and Q haven't changed. What that means is that sine of x and sine of x plus 2 pi are the same. Of course, I could have gone around the other way. So, in other words, if I, instead of going around anti-clockwise, I had gone around clockwise like this, then I would have decreased x In other words, x would have gone to x minus 2 pi, and that doesn't change anything because the values of p and q haven't changed anything. Of course, exactly the same argument can be made for cosine of x, which is cosine of x plus 2 pi, and that's the same as cosine of x minus 2 pi as well. And instead of 2 pi, if I had 4 pi, 6 pi, minus 6 pi, minus 2n pi, in all cases, sine of x plus 2n pi would be the same as sine of x, where n is either 0, plus or minus 1, plus or minus 2, etc. Let's now look at the graph of sine of x. X is, of course, going in this direction to the right, and we've already got the values at 0 and at pi by 2. And you see that it goes through 0. At pi by 2, the value of sine of x is 1. At pi, it is 0. At 2 pi, it is 0 again, because remember, it's come back to its original position, and now it keeps going on. If we decrease x, then of course it'll go back like that. Let's now plot sine of x and cosine of x. So you see over here that when x is 0, sine of x is 0, cosine of x is 1. As x increases beyond x equals 0, and we come to pi by 2, well, at pi by 2, sine of x is 1, but cosine of x is 0. At x equal to pi, sine is 0, cosine is minus 1. And as x increases further, well, we have the values repeating themselves. You see that whenever cosine is at the maximum, sine is 0. And when sine is at its maximum, well, cosine is 0. And that there is a phase difference of pi by 2 between sine and cosine. Finally, let's look at tan of x, which of course is sine of x over cosine of x. Whenever cosine becomes close to 0, then tan of x is going to go scooting off to infinity, either in the positive or the negative direction. And now let's look to see what actually happens as we go from x equals 0. Well, when x is equal to 0, sine of x is 0, cosine of x is 1, tan is 0. But then as x increases, then sine of x increases, cosine of x decreases. When cosine of x becomes 0, and that happens at pi by 2, then tan of x goes scooting off to positive infinity. Well, what happens as x becomes bigger than pi by 2? In that case, sine is positive, cosine is negative, and so what we are seeing now is the function tan of x becoming minus infinity, going to 0 at pi, and then increasing when x is equal to 3 pi by 2, it's infinity again. And you see this repeats. Let's go back the other way. Let's now plot this rather interesting function sine of 1 over x. Now you see 1 over x can become very, very large. But let's note the following, that sine of 1 over x can never exceed in absolute value 1. What that means is it's got to be lesser than or equal to plus 1, and it's got to be greater than or equal to minus 1. Another way of saying that is sine of 1 over x magnitude has to be lesser than or equal to 1. This is the second point I want to make. When is sine of 1 over x equal to 0? In other words, what are the values of x such that this happens? Well, of course, there is the possibility that if x is either very, very large or very, very small, then sine of 1 over x is 0. But there are other values for which sine 1 over x is going to be 0. And if 1 over x is either pi, 2 pi, 3 pi, etc., then it's going to be 0. Of course, if it's minus 1 pi or minus 2 pi, minus 3 pi, then it's also going to be 0. In other words, 1 over x equals n pi for n equal to plus or minus 1, plus or minus 2. These are all zeros of sine of 1 over x. Okay, so let's look at the difference between two zeros of sine of 1 over x. One zero is here. The next zero will be at n plus 1 pi. And if you take the difference, then obviously you're going to get 1 over n into n plus 1 pi. So you see, as n becomes larger and larger, the difference between two zeros of sine of 1 over x is going to get smaller and smaller. What that means is that if one looks at these points where the function is 0, they're going to get very, very, very cramped, either on this side or coming in from the positive side. So let's say that this is 0. So here's a 0, here's another 0, here's a 0 which is getting close, and now the next 0 is going to get still closer, and so you're going to get lots and lots of zeros packed near x equal to 0. You should therefore not be surprised at this plot of sine of 1 over x. Now let's understand this in some detail. We see that on this side here, the function is going to 0. In other words, as x becomes larger and larger, it's moving off to 0. Its maximum value is always 1. Its minimum value is always minus 1. It first went to 0 coming in from the right here. Then it went to 0 again over here, and again here, and then the zeros got so close together and they couldn't be drawn separately from each other. The same thing happens on the other side. Now, I just want to remind you that the distance between two zeros is 1 over n into n plus 1 pi. So clearly, this is a function that's oscillating very, very fast in this neighborhood over here. As our final example, let's take the function f of x, which is defined in this very peculiar way. It's 1 if x is rational, and it's 0 if x is not rational, or in other words, if it is irrational. So it's something that's jumping back and forth between 1 and 0 all the time. How does one even think about this function? Okay, so take any interval, let's say between 0 and 1. And imagine that we were to take, let's say, half over here. Now half is, of course, a rational number. Take any number over here, which is, let's say, close to half. It could be, for example, 1, 0, 0, 0 over 1, 9, 9, 9, 9, and that's going to be pretty close to half. So this number is here. But in spite of that, in this interval, there are going to be an infinite number of irrational numbers. So infinite number of irrational numbers. The picture that we have, if we were to try and plot this, would be a very strange one. So if this is x equals 0 and this is x equals 1, then the function is going to be 0 an infinite number of times, and so its value would be 0 for an infinite number of values of x, and its value is going to be 1 again for an infinite number of values of x. So here's a function that's wildly jumping from 0 to 1, back to 0, and up and down, and there is no way that you can graph this in a proper way. There's no pencil that can possibly plot this graph. As this last example showed, the smoothness of a function is something that needs to be very carefully defined. In the next lecture, we shall take up the concept of continuity of a function at a point.